go to the whiteboard, go to the share screen. Yep. Just last few questions, 2019. Let's move backward. We are dealing with the Bohr model, right?
I don't remember.
You can't remember the atomic model. After this, the mass is Bohr model, I think. Not this one. Or this one. So we are basically dealing with Bohr model or atomic model. I can't move this. Move this. Where's my mouse? Do again. SDK, optics. Yep. So this is the Bohr model. Yeah. So last time we derived this formula, right? We derived this formula, Bohr model. So basically, we are going to use this formula to explain the wavelengths. Can you see in this table, they have different wavelengths detected at different between different energy level. Do you remember? So basically, Bohr model tell us the energy formula for the hydrogen atom. Actually, it is for the, to be exact, it's the total energy of the electron in the hydrogen atom. This energy formula will give us we can write this formula so that we can explain the experimental observation. It's called the absorption spectra. Can you see?
Yeah.
I just write the result down. So basically, we have shown last time how to work out the energy level. So that is the total energy of the hydrogen atom. So H is a Planck constant, C is light speed, R is a Rydberg constant. The guy who actually formulated the formula, which can be written as this one. Can I write down here? So Rydberg write this formula down by using this, just multiply the constant. Can you see it's R, capital R? So Rydberg write this formula. Can we use their notation? They use P and Q. Yeah. So if we work out this formula, and we did this is first formula. The second formula we need to derive is the second one. So this formula can be written as, which is the final, which is P and Q are quantum number of upper. So P is upper, Q is lower. So Q is lower. So the Q takes the uppers because this is a fraction. Can you see? For the fraction, the larger the denominator, the smaller the number. So we are going to use the first formula to derive the second. In this case, lambda is wavelength. Do you remember?
Yeah.
Well, lambda is wavelength, and the Q and P are constant. So P and Q is equal to the integer. So you use notation that's integer. What integer? Integer is z, right? It's integer. So in other words, Q, but in this case, we have to make sure P is larger than Q. So P is larger than Q. And P is equal to, depending where you start. So we can either start in, let's just talk about Q, if you want Q. So Q is equal, the smallest of the Q is 1, you see? 1, 2, and 3. Once Q is determined, P must be larger than Q. Can you follow me now? So we are going to do, solve the second question. Can you see?
Mhm.
So let P and Q be a quantum number. So this n is called quantum number. In the first formula, n is integer from 1, 2, and 3. So n is called a quantum number. But in the second formula, we use P and Q to represent the integer. That's all.
Mhm.
And the level of the electron transition in hydrogen. So basically the final means, so if you want to know, apply this formula, you have to probably that it would be helpful if you know the diagram. Can you draw an energy diagram? Do you remember we draw this diagram using the first formula? That is energy level. And so the lowest one, can we say use different color? The lowest one is here. And after that, it'd be quarter. You see? Do you remember this energy level we did?
Yeah.
Yeah. So this is not a real scale, but if you use real scale, the upper level will look very crowded. So we prefer use this. So it's a sketch. It's n equal to 1. So n equal to 2. N equal to 3. N equal to 4. Can you see that?
Yeah.
So so the lowest one will be HCr when n equal to 1. Do you agree? The second one will be HCr divided by 4. You see, because n squared, right? And so on. You can write. You don't have to write all. So the experimental observation is here. So if you draw the some experimental observation, that is, can we use this part? So this is an experimental observation, right? We just draw a few. I just make a few colors. This is a red color. This is a purple one. Okay, the purple one, and there are other colors in between. The green one, blue one, yellow one, some here. So that is a spectra we can obtain if we just use the bright light here. So we got this, we can get this dark line, although I use bright, but it's dark, all right? So this wavelengths, oh, by the way, another diagram. We use horizontal axis represent the lambda, the wavelengths. Can you see? So this is just one of lambda, can you see? Lambda, this is lambda, lambda, can you see? These are all lambda, different number. Now, these numbers, there are many of them, can you see? They have different set. Actually, they're in textbooks, it's called different series, right? So if we pick up the Q, P is larger than, smaller than 6. So basically, if the formula for each lambda, according to the second formula, it's called Rydberg, who worked out this formula before Bohr. Okay. But we know that this formula can be used to find the formula that relates the wavelengths of light emitted such transition. Okay, so we just pretend we don't know the second formula. We are going to use the first formula to derive it, right?
Yeah.
How to do that? So according to the because if there's a photon, can we just if there's a photon coming, the carries energy h multiply f, right?
Yeah.
So if the electron is originated here, will be absorb this energy and jump. It's called a transition, go to up level. Can you see? Just like stellar. This is like photon electric effect. When they catch up some energy, they can jump. Okay. How far it can jump is will depend how much energy they absorb from photon. Right. So this process, according to energy conservation, so the energy electron absorbed were equal to the energy change. So that is a final, which is final. PQ, let P and Q represent upper and lower. So Q is lower, say Q is lower. So that we could P take the Q, you see? You follow me?
Yeah.
So in this case, in this particular case, P is equal to, sorry, the Q is equal, this is Q, can you see? This is P, can you see, in this particular case. So can you understand this formula now, the third one?
Yeah.
Okay. So this formula is just use the energy conservation. So energy, electron, how much electron energy can absorb depending on how much they can the photon provide, right? Now, if we just, they are looking for the formula of 2, okay? We pretend we don't know the formula 2. So what can we do? We can use this form, we can substitute the formula we just derived. Can we just replace the first formula by the energy level, negative hc, the constant, divided by p squared?
Yeah.
The second one, be careful about this negative sign here. It's still the same, hcr divided by q squared. Can you see?
Yeah.
So we just use equation 1 we derived. Now, if you just simplify this, then we can we put the HCR, factorize this factor, you see? And we just put we'll put the second term in the first. Negative multiply negative is positive, can you see? That is the Q square. And the second one, is, we'll put the first one to the next one is just minus P square.
Yeah.
P square, sorry, can you see?
Mm-hmm.
So if you compare with this, or another way you can do is to use a third formula. That is, you know, the formula, the light speed of light is equal to the product of lambda multiplied frequency, right?
Yeah.
And from here, we can work out that CF is equal to 1 over lambda, you see?
Mm-hmm.
That's right. So if I just rewrite this formula, so this part will become H3 divided by lambda, can you see?
Yeah.
Can you follow me? So HC, just in other words, this one will equal to this one. Can you see?
Mm-hmm.
Okay, and a little bit of algebra. So what do? You just cancel this. Can you see? HC. So in this way, we derive the formula originally, which was derived by Rydberg before Bohr, 20 years before him, or more than 20 years before Bohr. So that is R, can you see? Which is our equation 2. So that is something you need to know. You see? Now, in this case, we always use this relation. So P is larger than Q. Q is the smallest one is 1. Okay.
Yeah.
So we've done it. So this is a B. Can you see? So this is question B. Can you see?
Mm-hmm.
Now we're going to go to the question C, the last one. We just found some space here. So basically, in this C, can you read the question? They are looking for, they are trying to find this. So this is a table, and in which there are many wavelengths. Can you see? Then the unit is nanometers, and each of them have different P. Can you see? So P and Q. So P can the number. Can you see? This is exactly. Oops. Can you see the number of Q? Sorry, number of P. P is always equal to larger than Q. So this is one, 2, 3 different P. Can you see?
Mm-hmm.
Now, what are they going to do? They didn't tell you the Q, but they tell you the wavelengths, right? They tell you the measured wavelengths. So for each of the 3 hydrogen emission line sets, in other textbook, this set is called the series. Okay, called the series. shown in the table below identify the quantum number and of its lower quantum Q. Or Q is to be determined, can you see?
Uh-huh.
And each set column. So basically we know P. We have used the new formula we just derived. Each set column 5 emission line has been the same lower energy. They share the same energy. Can we just draw one of them? Can you see? If Q equal to 1, if the Q equal to 2, put in the color. So if Q equal to 2, so what is P number? P will equal to 2 plus 1, can you see? So that is equal to 3, can you see?
Mm-hmm.
And the next P is P equal to 2 plus 2 equal to 4, you see?
Yes.
So in other words, so this, if I just continue to draw that, so that is one of a series, can you see? It's one of them when Q equal to, when Q equal to 2, not equal to 0. All right. But in this case, they didn't tell you the Q, right? You can't use this formula. So in principle, we can set up many equations. Can you see?
Mm-hmm.
For example, they just ask you to assume P is less than 6. All right, P is less than 6. If P is less than 6, what is the Q?
Less than 1.
Yeah. P
So
is 5. Q is less than 5, isn't it? Q is less than 5. Do you agree?
but if Q is equals to, for example, 4,
Q
then
is
at the very bottom of the graph, the P value will be 9.
and let's just read the question. So P is smaller than 6. So what is the Q from this condition?
In the bottom line, it says Q plus 5. P equals Q plus 5.
Yeah, P is yeah. So this is P. So P1, can we say P1 is equal to Q1, right? Can you call that P2 is equal to Q3?
So P5 equals to Q plus 5.
So that is
So Q must be smaller than 1.
Yes, can we just write down here? So that's the 4. There are 5P, right? There are 5P. And P is less than 1. P is less than 6.
Yeah.
What is Q? Q is 1.
0.
0. Q cannot equal to 0. That's unfortunate.
But it can't equal to 1 either.
If that's very interesting. So let's just look at this formula here. The smallest one is 1. Okay, so this is smallest. So how can we determine the relation? So what is the question? Each set and 5 emission, yes, has the same lower energy. Okay, so once we know which is lowest, we can solve this question, right? The first column showing the quantum number upper is P, right? Relative to lower level. So Q is lower level. Can you see? We just draw a diagram here. Can we? So this is a Q, right? So this upper level is upper level. How many steps? 1, 2, 5, right? So this is a Q plus 1, right? You need to is Q plus 2, right? Q is less than 6. What does it mean? What is a Q? What is range of Q? So they are all Qs, right? Q plus 3. Yeah, the way they're asking is a little bit strange. And until Q plus 5, right? Now we have constraint. First of all, Q must be equal or larger than 1. That is constraint. We cannot choose Q less than 1, right? So in this case, what is the Q?
It's not possible.
This is a very strange question.
Mm.
You may assume that P is less than 6. If P is less than 6, so Q is not larger than 6, right? Let's just try it. Let's just try it. So if that's very strange question. Can we just draw this diagram again? So if this 1, 2, 3, 4, 5, 6, sorry, this is 1, 2, 3, 4, 5, right? So this is less than 6, because this is 5. Can you see? This is 5. This is 4. This is 3. This is 2. This is 1. This is impossible. Can you see?
Yeah.
Q means Q0, because there's something wrong with this assumption. Okay.
Mm.
Can we just without doing this? Can we just write? Can we just use algebra to solve this puzzle? Right.
Okay. I don't get what does set ABC mean.
ABC is the different starting point of the Q. So this is a Q. Can you see? So this is Q1, the lowest energy. So this is Q1, Q2, Q3.
Okay.
Can you see that this is one series? Another thing, I can draw another one if you wish. So if I just starting from the bottom, okay, there's another set. Can you see? Can you see? Another set can be drawn.
Mm-hmm.
Can you see? Now the yellow one, the yellow set, the Q is 1. Can you see? The white one, the Q is 2.
Okay.
That makes sense.
Yeah.
So you can say this is the lowest set, but we don't know Q, right? Why don't we work out this? Because each lambda will give us a Q. Can you see? Can I pick up this one? We don't follow their instruction. Can we pick up this wavelength? Can we? Right? If I use this wavelength, that wavelength will allow us to write this formula here using the formula we just derived. So 1 over lambda. So this lambda is 121.57.
Times 10 to the negative 6.
They use meters. They use meters. So we have power to time power 9 a second, right? Negative 9.
Minus 9, yeah.
Okay, that will be equal to this constant. Can you see? Just a constant. We know it's constant. That will allow that to work out the Q. Do you agree? This will be the Q, and that Q square, sorry. That equal to Q plus 1 square. Do you agree?
Mm-hmm.
Q or Q plus 1. Do you think you can solve this Q?
Yeah. I need my calculator.
Yeah, it's quadratic. It's quadratic equation, right?
This is
Can we just denote it as constant? Can we, if we divide it by R, can you see? Can we call this part is alpha, right? Alpha equal to 1 over Q squared plus minus, sorry, minus 1 over Q plus 1. How do we solve this equation Q?
I'm using my
Numerical calculator. Yeah.
Oh.
Q must be integer, right? Q must be integer.
Yeah, but it looks so complex. There's no solution.
No solution. Well, we can jump to, can we jump to the second lambda? We can try these three to see which one can allow us to work out the positive integer for Q. How about, can we change the value for lambda? Let's go to set B. Oh, this is longest wavelength. Shortest wavelength. Wavelength getting shorter. That's right. Yeah. So we pick up the shortest, longest wavelength. Longest wavelength is that's right. Longest wavelength. One of the three should give you a positive integer for Q.
Still no solution.
No solution for theta B. How about theta C?
Oh yeah, I tried to see. There's no solution. I don't know if it's the problem with too large numbers, so then like calculate the compressors.
The two numbers, one is very small, one is not. Can you see? Can we work out this alpha? So this R is here. Can you see? R is a huge number. 1, 2, 3, 4, 5, 6, 7, 8.
Yeah, but how do you do that in the exam?
Can you just work out this product for me? So how about lambda multiply R? They have three lambda 1, lambda 2, lambda 3. Are these a simple number close to integer or not?
Okay, I'll try.
Just found this. Can we pick up these three lambda 1, 2, 3? So this is 1, 2, 3. 1, 2, 3. Yeah, this is not integer, yes. So
Done.
is that possible to solve the Q numerically or not? Because you are not allowed to use calculator, right? Is there any algebraic way to solve that?
Yeah. Open up the brackets, but it sounds no, it doesn't work.
Oh, alternatively, can we we import a different Q to work out the result from this side? Can you see?
Yeah,
It's too hard to solve. We just set Q equal to 1, 2, 3. Just go up. Q equal to 1, 2, 3, 4, 5. Okay.
Okay.
So this is probably the quicker way. It's possible to use the calculator too. And we know the result. Can you see? We know, oh, that must be reciprocal of this number. All right. So this is our reciprocal, alpha -1. Can you see?
Okay. So reciprocal.
Because this alpha this represent lambda r. Can you see? Alpha represent 1 over lambda.
Oh, got it.
Aha, yes, 1.33, right? That's first one. Aha.
Yeah.
Okay, so that's probably the way to go. So you just trial and error. So this use this very primitive method, but sometimes work. So the objective is to determine the Q. We found it, right?
Mm-hmm.
So for the set one, Q is equal to what is the Q for one? Q equal to what? What is the Q for first case?
Okay. Q
You
equals what?
Q equal to one, right?
Yeah.
Oh, good. If you Q equal to one, you can try different Q. You can use different Q to compare with this reciprocal value. Oh yes, you got this first. Good. Very interesting. So the lambda is getting longer. The lambda so Q must be larger. Can you see? You can start a Q from 2 or even 3.
Yeah, I'm doing 4 right now.
Oh, you're doing 4 now. Good.
Yeah.
Wow.
Okay.
Oh, good. Imagine this is what Rydberg did over centuries ago in 1880 or something, 1850. It's amazing without a calculator. But he's doing other work. Universally, he work out as a constant. He knows this must be a constant. Can you see? The only thing in those days they know is lambda. They have measured the lambda, the wavelength. Wow, we have done that. Good. Right? Let's go to the next one. Oh, okay.
Yeah.
Good. Let's go to the next one. That's a large question. This looks like geometry, right? Do you want to try the geometry? Just found the formula for a particular area or variable. So it's got a circle in a square, right? Circle in a square. Find expression for theta in this diagram, which the gray area AG is F times of area of the outer square. AS, outer square, AS. So which is one? What is the gray area? F time. Yes, that's the first equation. Your expression here should take the form where B is constant. Yes, CF is function of X.
It's the area of the outer square.
Yeah, what is outer square?
The whole square?
The whole square, right? Okay. So you have introduced, oh, we know the size. Size is 2R. Sorry, 2XR. 2R or 2XR? 2XR, right? Can
Which
you?
side?
So this side, can you see? If we call this side is A, that's a 2 multiply XR. Can you see?
Yeah.
That's the diameter of this larger circle. So that so-called outer space is just A square, right? Is AS is A square? Okay, so that is your first equation. This is the first equation. Yeah, it's actually just an addition of subtraction of this area, right? regular area. So that is AG, or AS rather, AS. AS. Okay, how can we find the gray area, shaded area? It's just difference, right? It's just difference of this circle. Can we just extend that straight line here? Can you see?
Yeah.
That's probably easier for you to read. So the gray area, you have to, there are two circles here, right? You have work out, oh, very tedious. What
B.
yeah, sorry?
What's B? B constant and CF is a function.
B and C are explicitly, and C are explicitly, you are. So B is a constant. Just you can doesn't matter. You can work out this constant. You can use other notation, but in this formula, so basically they are just trying to prove the formula for theta is equal to this position. We have Cx here. Can you see? We got the one variable which is x. Can you see? Well, so this is what we need to use, x squared.
Yeah.
But what is f? Or f is how many times of the area? Okay. Now, before you go further, can we work out as a gray area? That you need to work out this area formula first. It's difference between several things, right? It's equal to the square area. Can you see? Take the circle. Can you see?
Yeah.
If I'm right, take the circle. That is xr square, and edit that inner circle. Can you see? Edit the inner circle. Can you see that? Edit the inner circle, and also you have added this area. So that's very hard. You can see this. You have added the difference between the two. Can we just highlight this one before you go into calculate? You have to work out this one. Can you see this sector? Can you see? You can try that. So that is theta is given. So you have the added this larger one and subtract this one. You have to subtract this one. Can you see? I use different color. You have to subtract this blue one. So the green one, can you see?
Yeah.
That's sector. Oh, have fun.
I'm so tired today.
Okay, I'll show you. My brain works now. Okay, can we just can you see we take this large circle, right? We take a large circle, but we must put this short circle back. Okay. In the meantime, we have found this area. So this area is what we need to find out. Can we this shade area? Okay, so we have worked out this another one. Can you call this area? Can you see? Just call it 1A. So A is difference. Can you see? A is different between the two. One is pi r theta, right? The theta about put it theta divided by 2. Can we factorize this one? We have used the difference. Can you see? The first is pi r square. We have used x r square. Can you see? Take the r square. Oh, that's it. You follow me?
Yeah.
So this is a second equation. This first. It's called 2. It's 3. Okay, so factorize r. Can you factorize r? We still got r squared. So r is constant, right? R is constant. So theta is to be formulated. So inside, oh, we got this x squared minus 1. Oh, we got this factor now. Can you see?
Yeah.
So can we use this side? This is 4, you see. So can we find the formula for theta first? Can you see?
Yeah.
So from this formula, this we can solve this A. Yeah. Can we solve this A from this formula?
So for A.
Yeah, we because this A includes this theta, right? So we can substitute 4 in replaces A. Can you see?
Yeah.
In the first equation. That's right. So we get something closer now. And another thing is x squared. Can you see they get x squared term here? Can we just, oops, what did I do? Okay. You can put this as constant. Can you see? Can we put this x squared outside? This one looking for this x squared. Can you see?
Mm-hmm.
We got x squared divided by x squared. Yes. So can we put all this area on the other side? Can we? Well, we still have x on other term. Well, be careful. Can we rewrite this one as a 4? Just use your color. What is the red color? Can we just rewrite it as we use equation 2? 4 multiply f. Can you see? We got another x squared here, and r squared. We put r squared here. That is a left-hand side. You see? So what is as? As is a squared. Can you see? as is just they got x squared as well. Do you remember? That equal to x squared pi
R squared.
Capital R squared, right? That is
Yeah.
as. So we just put x squared outside. That became pi r squared x squared. Can you see?
Yeah.
And this constant term. So this is what we call the constant. Can you see? Pi r is constant. Yeah, we're getting there. So that is that's constant term. So in this formula, we got they got factor. We can factorize r squared. Can you see?
Yeah.
We got to factorize r squared. So therefore, we got theta multiply x minus x squared minus 1 divided by 2 pi. Okay. Divided by 2 pi. So that's good. We can cancel this r squared. Can you see?
So this one cancel out.
Oh, good. Oh, yes, that's canceled as well. Good. Oh, that's quick now. Oh, yes, we're nearly getting there. Do you want to continue? I think it's very simple now. All right. If you are, if your brain works, and you can easily solve this problem. All right. So
They cancel out.
they cancel that part. So this part canceled.
What are we looking for? This
We're
one.
looking for theta. We just need to solve the theta.
Is this
We
3?
need to find the formula for theta. Can we just arrange that theta x squared on the left hand side? Can you see? We just equal to 4f minus or pi minus 4f. Yeah, pi minus 4. Yeah, you can try. Yeah, nearly. We nearly get there. Yep. I think that's what I'm looking for, right? Another thing you have to make sure this is the B is a constant. CF is a function of F. Yeah, we get a CF, but state B and CF explicitly. So they have to work out what is A, what is C, what is capital B, what is C.
Mm. So we
Nearly,
need to
yeah,
move the x squared out.
yeah. Well, sometime we maybe next time you can when you can work out again. It's no point to keep going, right? Because
Okay.
we have trouble here because we got we these b's got we got this form, so we have trouble here because x is a variable, right? So maybe
No.
we'll have checked what we have done, all right, before we go further. But roughly it's correct. Can you see?
Yeah.
We got this factor now, but we have to make sure how do we work out the b. Okay, what is the b? B is a constant, they say. All right.
Oh.
Okay, let's stop here. There's no point to solve this now. All right.
Okay.
Because we know the direction to go. Let's save that. Go to next one. Yeah, we need to finish. Oh, that is a simple one. You know this you know how to do that? It's simple, right? Do you know how to solve this one? Exponential. I think we have done this before, right? You can convert into quadratic equation. Do you remember? Do you remember how did you solve the problem? Connection. We lost the connection. Okay.
All I can think of is rearranging it.
Yeah, just EX. We can multiply. Can you see? We multiply, that will become the e negative x
Yeah.
plus 10, right?
Yeah.
And what we do, we got two terms. So we got if you multiply if you put them together first, you can see the x take 2e negative x and minus 1 equal to 0. You see?
Yeah.
So we got x with x here. Can we? You can multiply. Yeah. Can we multiply x negative or whatever? If you multiply x negative, can we multiply x negative x? So the first term is 1. Can you see? The second term is become the e negative 2x. Can you see? The third one is just e negative x. Can you follow me? Quadratical. Can you see the quadratic equation now? No? Not yet? Can we put this e negative x?
What did you time from this one to that one?
I just multiply. Can you see? I multiply e to the power negative x.
Oh, multiply e
okay.
To the power. Okay.
So this I put it to the other side. So this negative doesn't matter. This negative we can multiply negative 1. We can multiply negative 1 to make it positive.
Oh, I see.
So that is e negative x. Can you see?
Yeah.
And the minus 1 is minus 1. That's quadratical. Can you see?
Yeah.
So that is you can introduce the u, right?
Yeah.
So that is easy for you. I think you solved this problem before. Quadratical from.
I remember doing the u substitution, but I don't remember doing the times e to the power of something.
Oh well, you can multiply e to power positive as well. Doesn't matter.
Oh.
Yeah. So that is how to solve that. Let's save this and clear and go to next one. Let's do this one. Nearly finish. Oh, not yet. What's this question? Firework, rocket, launch vertically. So this is you can draw this diagram. Let's draw some dark background. So bright. You can just make a dark background. So this is looks like mechanics, right? Like a conservation law, how to apply conservation law here. Because that rocket is divided into several parts. Can you see? Have you read the question? So basically, they have the rocket. This is a rocket. So this is a rocket, the launch the rocket vertically. At the moment, this explosion. It
Yeah.
move with the vertical speed. So at a certain stage, explode. So at this moment, the vertical velocity is given, right? So the we know is given
Yeah.
is 2 meters per second upward. Explosion release energy of that much. That energy released, and the rocket burst into 4 pieces. Wow, 1, 2, 3, 4. Wow, how can we draw the 4 pieces? The pieces with mass 4 move vertically upward with a speed equal to that. The pieces mass 3, 2, and 3 move horizontally. The pieces. So basically, what happens is that this initial condition, right?
Yeah.
After that, this initial, this become 4 pieces. Can you see? So they become 4 pieces. 1, 2, 3, which is which? The piece with 4 mass vertically upward. So this velocity 4, right?
Yeah.
That's a 4 with mass 4. And 3, which is horizontal. The piece with 4 move vertically with that speed. The pieces of 3 and 2 move horizontally. Doesn't matter which direction. I can't hardly read this, too small. Horizontally, and the piece of mass 1 move vertically. Vertically must be downward, right? The mass 1 must move downward. Can you see? Or not necessary because they are moving together, right? So we don't know the direction of mass 1, but we certainly know there's 2 velocity. One is called V2, another called V3, all right? Yes, so certainly we can apply certain conservation laws such as momentum and kinetic, right? So there are 2 conservation laws you can apply. Can you try? So this is initial. So this is
I was thinking about
is initial. Is the final state.
Yeah.
Okay. Obtain the speed of all pieces after explosion. All right. Velocity and the direction of this question is given relative to the ground. Okay. Your answer should do the same. Okay. Obtain the pieces of all pieces after explosion. What is rho? Rho is what is the rho?
momentum.
We use a P. You use we use a P. P is for density.
Okay.
Can you use a P? We can use P instead. Okay. So that is can we just write the formula first? Okay.
Yeah.
So the total initial momentum of this system is they just upward, is upward, okay?
Yeah.
It's upward because that is can we just call this X and Y direction as the Y direction is X. So this momentum is Y direction, right? It is a Y direction. So this is a PY, PY. Oh, we just write the total mass, right? This is total mass, which is in the direction of upward. Okay. So this must be equal to the sum. Can you see this total? So this is the initial, right?
Yeah.
So base can write a conservation law now for the momentum. So mv law must equal to the sum of these 4 and 1, right?
Yeah.
1 v1. But we don't know the direction, right? Probably they are, or maybe they are different, but we don't know. We will see. If we got a negative, that would be that assume our that imply our formula, our assumption is wrong. Okay. And on the other hand, the horizontal directions is 0. Can you see? Horizontal direction is 0. So therefore, M3 V3 minus M2 V2 is 0. Can you see? That is two conservation law. That's momentum conservation, right?
Okay.
So that is first. So first we use the momentum conservation. So the momentum conservation. Another formula we can use is energy conservation. So the second formula is energy conservation. So how much energy initially? Energy conservation.
1 joule.
That's released, right? There's additional formula added. Conservation. Initial one is a kinetic energy. Do you agree? That is a total mass. That is a total kinetic energy initially. That is a mass to the V naught square, right? In addition, they have extra explosion release the energy. So that is due to from other say, chemical energy, right? So you have to add this energy. Can you see? That is initial. That's called explosion, EX or EXP. That's initial, right?
Yeah.
Now, how about the other? So we got a lot of term here. M1, V1 square, right? And half M2, V2 square, and 4 pieces, right?
Yeah.
Wow, that is complicated. 3 square, and the ninth finally is a half right down here. M4 V4 square. Wow, we got 3 questions. The third one is complicated. Yes, can we just cancel this half? Can you cancel this factorize half first? That can simplify the question slightly. Wow, we got 3 questions. How many unknown? We have 4 unknown, right? 4 velocity. How can we solve this question? We have 3 questions only. Double check. Oh, we got a velocity. We got V4 is given. Good. Can you see? V4, we got 3 unknown. Okay, so V4 is given. So this, sorry, this is 4. So this is given. Can you see? We know this V4 is 4 gram. Gram. They have they have convert gram into international system. But doesn't matter. We can solve this question now. Can you see? This is just number. Can you see? Or can we put this together? So in other words, so the sum, because basically we know that M1 V1 square plus, we just put them together, M2 V2 square plus M3 V square equal to this sum. Can you see? That equal to M4 V4. We know this term. Can you see? And take this M V naught square and oh, hang on, minus who? Oh, sorry, the sign is wrong. Hello, it's connecting disappear. Is hello? Yes, disconnected, right?
I was lagging.
Okay, I just read this formula here for you. So we got M V naught square plus explosion. That's just extra energy provided. And take M4. They just constant. Okay, V4 is constant. Can we call this constant? Can we call this A? It's just constant, right?
Are they given?
Yeah, this is all given. So it's not very difficult, not very difficult now. Obtain the speed of all velocity. Okay. So we just probably, do you want to go for it further or want to stop here? Because
My brain is so tired.
yeah, okay. You are tired. So we stop
Maybe
here,
next
all right?
time. Okay.
Okay, stop here. So nearly finished. Can you see? We got, I just highlighted this formula. You can have a look. So we got this two formula here and one formula here, all right? So I'll see you next time. I will save that.
Thank you very
Good sleep.
I'll go to
Okay.
bye-bye.
Goodbye.